Good afternoon, guys. So this video will just do a few problems on momentum and collisions. There is a particular problem I want to work with you guys right now, which is very similar, if not identical, to the Weber sign. And just for calculation purposes, I'm going to assume a value of gravity that in university, we don't really use it. I haven't been using it with you guys in this online setting, but just to make it quicker, so you can see what's going on, I will do it, but don't use it in the Weber sign. You have to use 9.8. So I will use 10 meters per second squared, just so I can show you this problem. 9 kilograms. So I'm using very similar values to the ones in the homework. Uh, 5 meters. The block is going to be released. There's going to be a collision, and obviously this block will go to the right, and the other block, the purple one, will recede. So the problem is asking you, by how much will it recede? So how much will this block will go back up? It's a classic problem of collisions, and very easy. This is a rest. So there's also a rest, but as a no friction, okay? So mu equals to 0. As the block comes down, this block will gain some speed. How do we get the speed? By conservation of energy. The potential energy is going to be equal to the kinetic energy where? Exactly before the collision. Here. Right? There. Let's put here some B1 initial. So, and this will be D2, right? Mass 5 kilograms times gravity, I'm using 10, times height is equal to 1/2 mass times V1 initial squared. 5 and 5, 2 times 5 is 10, times 10 is 100. V1 initial square is 100. Then V1 initial is equal to 10 meters per second. So that by itself could be a problem from chapter 7 and 8. Chapter 9 is about collision. So for the collision, before and after, we have conservation of momentum. So for the collision, we have that momentum before is equal to momentum after. But these are vectors. So this speed is also 10 meters per second to the right. So momentum before is just the momentum of the 5 kilogram block. 5 times 10 plus 0, no momentum because it's a rest, is equal to the momentum after. After the collision, the second block will move with B2 final, and the purple block will recede with B1 final. That's after the collision. So 5 times B1 final plus 9 times B2 final. Now, we have two variables. But we also know this, right? B1 initial plus B1 final is equal to B2 initial plus B2 final. Yes, we are going to, in the problem it says to assume this is an elastic collision, okay? So, yeah, elastic collision. So we can use that relationship. We can rearrange this as B1 initial minus B2 initial equals to minus B1 final minus B2 final, parentheses. But we know B2 initial is 0. B1 initial is 10. 10 is equal to minus B1 final plus B2 final, right? The minus gets distributed. And this equation gives us 50 equals to 5B1 final plus 9B2 final. Clearly, I can eliminate B1 final if I multiply the first equation by 5. This will give me 50 plus, if I add the equations, right? If you add the equations, 50 plus 50 is 100. This will be minus 5B1 final, 5B2 final, minus 5B1 final, 5B1 final, 5 plus 9 is 14B2 final. Perfect. So B2 final will be 100 over 14, which you can approximate to 7 meters per second. So B2 final is 7 meters per second. Where here. So B2 final all here will be 7 meters per second. Right? There. Is that the end? No. I need to find B1 final. And I have everything. I can use this equation. B1 initial is 10. B1 final is what I want. B2 initial is 0. B2 final is 10. So clearly, let's do it on the other side. So I'm gonna move this there like that. So here, right? B1 initial plus, that's not very clear, right? Let's just do it here. B1 initial plus B1 final equals to B2 initial, B2 final. B2 initial is 0. This is 10 plus B1 final equals to 7. Therefore, B1 final is equal to negative 3 meters per second. What's the meaning of that negative? Means that it's going to the left, and that checks. So now the last part of the problem. In the last section, we have that the mass, right? We have this graph, this mass of 5 kilograms is going to start receding with 3 meters per second. So it's obviously going to get to some height, h. Right? It's going to go like this. If we can ignore friction, then we can say that the kinetic energy is also equal to the potential energy. There. The kinetic energy is 1/2 of the mass times 9, v squared equals to mass times gravity times h. Mass, 2 times 10, oh sorry, h, right? 9 over 20. So 4.5 divided by 10, 0.45 meters. That's h. .545 meters. So the mass recedes just a little bit, right? Because most of the speed was given to the 9 kilogram, 7 meters per second. Okay. All right. Let's do now a 2-dimensional collision. And it's a very easy problem. It's also similar to the one in the assignment, all right? Okay. So a 2-dimensional collision, I went over a little bit of that in the lecture, but I think the best way to understand that is by just doing a couple of problems. The thing is that it's better. All right, so let me just take a look at the values I want to find here. What happened? Okay. Again, it's a 2-dimensional collision elastic. So 2-dimensional you have a mass moving to the right with, say, 2 meters per second, but the mass is of 0.3 kilograms. And this is 0.3 kilograms. But there is a mass here, just on the side. And this mass is of 0.5 kilograms. That's before the collision. After the collision, well, just as you expect, yeah. So there's going to be a collision. So after, you are going to have this line is going to be like your reference, because you are going to have a line of sight like this and a line of sight like this. You're going to have this mass 0.3 kilograms moving with some speed, velocity, and they tell you it's 1 meters per second. So that's the thing about this problem. They tell you that, and they give you this angle, 50 degrees. And this velocity is also given. No, it's not given, sorry. You want to find it. This is 0.5 kilograms. All right. That's the only information you are given. You want to find the velocity and the angle. What's the angle here? Let's put angle theta. So in a two-dimensional collision, you also have conservation of momentum. The momentum before is equal to the momentum after the collision. The momentum before, again, is a vector, 0.3 times 2, and 0.5 times 0. This is a rest. So 0.3 times 2 plus 0 is equal to momentum after. The momentum after has two components. Has the x component, but you also have the y component. So this one is on x. This one is on the positive x-axis. So I need to have the momentum there on the x-axis, which will be this one multiplied by what? The cosine of 50, right? In fact, in the problem in the web assign, they give you that. So they give you those components. So you have here 1 cosine 50, and you have up here 1 sine 50. But down here, you have, this will be V2 final cosine theta, right here. V2 cosine theta. So here you will have 0.3 parenthesis 1 cosine 50 plus V2 final cosine theta. But what about y? I'm going to make a graph so you can see it here. On y, you have this. You have a mass of 0.3 kilograms going up with Vy. But that Vy is 1 sine 50. And you have a mass of 0.5 kilos, which is going down with V2 sine theta. The momentum also has to be conserved. So the momentum going up has to be equal to the momentum going down. That's it. So here you will have 1 sine 50 equals to V2. Sorry, mass times, oh my God, mistake there, kilograms. 0.3 times 1 sine 50 equals to 0.5. V2 final sine theta. This is B2 final, right? Two equations, two variables. Let me show you how you're gonna solve them. 0.3 times 2 is 0.6. So I can rewrite the equations as 0.6 equals to, okay, cosine 50, you have to use a calculator for that. And you're gonna multiply that by 0.3. So cosine 50 is 0.64 times 0.3, that's 0.19. So yeah, let's put 0.19, so 0.60, 0.19 plus B2 final cosine theta. If I do this, that will be 0.41. So 0.41 equals to B2 final cosine theta. And this one here will be 50 sine 50 times 0.3 divided by 0.5, 0.46. So what happens? I get 0.46 equals to B2 final sine theta. Two variables, two equations, and that's perfect. That's the perfect setup because I can divide these equations. This is the bottom divided by the top. 0.46 divided by 0.41. You cancel this and you get sine over cosine, tangent of theta. How much is theta? Well, .48 degrees. Perfect. .48 degrees. If I have theta, I have B2 final, right? I can use this equation, for example. Where can I show you this? Let's leave that in here. Here is the setup of the problem. Let's erase this. 0.41 is equal to B2 final times the cosine of 48. So B2 final is 0.41 over cosine of 48. .61. Okay. All right. What other things you can be asked? You can be asked the change on kinetic energy, the kinetic energy at the beginning, and then compare it with the kinetic energy final. The kinetic energy at the beginning will be mass times velocity squared divided by 2, which will be 0.6 actually, joules. And then this square times mass divided by 2 plus this square 1 times mass divided by 2. You add them together and then you get the total kinetic energy after the collision, and you can compare it with the kinetic energy before the collision. But that's how you do two-dimensional collisions. Nothing. There is other type of problems, by the way. Yeah, there is the problem of the billiard. So let's leave that in there for a bit. The other problem you can have is just one mass going at some angle and then bouncing back. All right, that's a very nice problem. Let's have to remember if you need two angles. So you have this and you go like that, you may not need both angles. Let's take a look. Let's explore that problem. And I will do 2 more after that. Okay? Well, it's recorded, so you can always go back and check. I'm gonna leave this for a bit so you can see it. The problem I was talking about with 2-dimensional, with one mass, will be if I give you the billiard problem. So you're given an axis of reference, and then you have a mass, which is coming at certain velocity to this point, and then it's gonna bounce back. Okay? Yeah, so let's change the angle then. Let's make this angle 53, and let's make this angle 37. Yeah, so if that happens, what should be this V2? And this is V1. It's the same mass, so the mass here is of, let's say, 0.4 kilos. And V1, should I give you V1? Yeah. 2 meters per second. Pump it up. So obviously, y-axis, x-axis, 2 dimensions. Just one mass though. Okay. So I always notice that there is like a glare in there, but you can see the numbers there, right? Okay. On X, mass times V1 initial on X equals to mass times V2 initial on X. So you may not even need V1. Let me see. Because you have this angle. Yeah, you don't need this angle. It's too much information. Yeah. Yeah, too much information if I give you the angle there. Because you see what happens is that the mass will cancel. But what's V1x? You have V1 on this direction, but also going like this. And here you have V2 on this direction, but also going like that. So this is V2y, V2x, V1y, V1x. So V1x, V2x. V1x is 2 cosine 53. And V2x is V2 cosine theta. There you are, that works. So 0.4. What's V1x? 2 cosine 53. Equals to 0.4. V2x is V2 cosine theta. That cancels with that. Cosine 53 is 3/5. So 6/5, which is equal to 1.2, is equal to V2 cosine theta. That's your first equation. Now let's take a look at y. Just like the last problem that we did, right? The one that was with the two masses. On y, mass 0.4 times V1y, so 0.4 times V1y is also equals to 0.4 V2y. So mass and mass cancels. V1y is 2 sine 53 equals to V2y, which is V2 sine theta. Sine 53 is 4/5, 8/5, 1.6. So what you get is this. 1.6 is V2 sine theta, and 1.2 is equal to V2 cosine theta. So what did we do in the last problem? We divide the equation, but now I cannot top and bottom, right? If I divide like this, V2 cancels, 1.6 over 1.2, that should be 16/12, right? 1.33 is equal to tangent of theta. So 1.333 is equal to tangent. And guess what? That, if I'm correctly, that should be also 53. Let's see. Yeah. So theta is 53 degrees. It's an elastic collision, so you expect that, right? There you are. Okay. So that's an easy problem as well with 2 dimensions. Nothing difficult. The momentum on X and momentum on Y. Okay. And the other problem I wanted to do now, let's go to total inelastic collision. Is there's a problem where they give you a bullet. So let me show you the problem. It's a bullet with a pendulum. So it's a collision, it's not a complete elastic, it's a collision problem. So the bullet pendulum problem. There are 2 types of these problems. I will do the other one on the next video. And then I'm gonna start talking about center of mass, all right? Next week, or when you guys watch this, after the next video, we will talk about torque and angular momentum, which will be almost the last topics of this semester. That's good. They tell you this, you have a pendulum and you have a mass attached. And you have a bullet that was fired towards the pendulum. Like that. The bullet goes through the pendulum. So, and it leaves the pendulum with velocity v/3. But because there's a transfer of momentum because of the collision. By the way, this is length L. The pendulum obviously is gonna go up. So like that. they are asking you what is the minimum value of that V of the bullet so the pendulum can barely go through that? Because there is a minimum value for that to happen. There you are. Right? Find the minimum V of the bullet. Let's first use conservation of momentum. The momentum before is equal to the momentum after the collision. So what happens is that the mass is going to acquire a velocity, velocity to initial. Okay? Mass of the momentum after, momentum before is equal to momentum after the collision. The mass of the bullet times V is equal to plus 0 because the first mass is not, the large mass is not moving. The momentum after will be big M times V2 initial plus little m times V over 3. If I do the math, I will get 2/3 of m, little m, is equal to big M times V2 initial. I have one relationship. They want the mass to reach the top with certain velocity, I'm going to call it V2 final, and in such a way that it will barely make the loop. There's a keyword there, right? First of all, how do I find V2 final? To find V2 final, we need a conservation of energy. Because the mass starts from here, this is your point of reference, and will reach a height 12. So the kinetic, for this mass here, the kinetic energy will be equal to the potential energy at 12. The kinetic energy is 1/2 of the mass of the big mass times V2 initial, which I have in terms of mm, right, is equal to the big mass times gravity times 12. Mass and mass cancels, and then from here, my V2 initial was 2 little m over 3 big M. So 2 little m over, or 1/2, 2 little m over 3 big M, that's equal to 2Lg. Sorry, my bad. What am I talking about? We have to add the kinetic energy at 12, which I will have to add 1/2 of big M V2 final square. There you are. So again, mass can cancel, right? So that's okay. 2m over 3m, 2 little m over 3 big M times this 1/2. That's equal to 2Lg plus 1/2 V2 final square. 2 and 2 can cancel. I multiply by 2. So I will get this. V2 final will be 2m, 2 little m over 3m minus 4Lg, the square root of all that. But hey, I need a condition at the top, right? There has to be a way to simplify that. To barely make it through the loop, right? At here. What's the condition? That the centripetal force has to be equal to what? To big M times gravity. The normal is 0. So it barely makes it. What's the centripetal force? M B2 final square divided by R, which is L. That's mg. M cancels, so I can put all that in there, and I will find a relationship. What are they asking? Let's go for little v. So little v, yeah. So I find V2 final. You want little v. Oh, sorry guys, I knew I was missing something here. So that happens, that's okay. All right. So what I ate here was the v. So there should be a v here, there should be a v here. Everything is okay. We just have to put a v here and obviously a v here. That's the one. That's what was missing. I was like, what's the variable they're asking for? They're asking for little v. So little v goes here, right? Yeah, that's okay. So I have V2 final square equals to Lg. Perfect, that will work. So, find the minimum value of V. V2 final square is equal to Lg. But V2 final is that if I square this, the root will cancel. V2 final square is that Lg equals to 2 little m over 3 big M times V, which I want, minus 4 Lg. Minus 4 Lg goes here as 5 Lg equals to 2 little m V over 3m, and I got the answer. My answer will be 5 times 3, 15 LgM divided by 2 little m. So here, V will be equals to 15 Lg big M over 2 little m. That's the answer. All right, so that's a very interesting problem, right? This problem combines chapter 6, chapter 7, chapter 5. First, we started with a momentum conservation, which is the easy part. 1 minus 3, yeah. Then I got V2 initial, which is the velocity as the mass goes on the loop. Then I know that the kinetic energy initial at the bottom is equal to the potential energy at the top plus the kinetic energy at the top. The kinetic energy initial is 1/2 m. Oh wait, V2 initial square. Ah, my God. I knew I was missing something. Well, if you are watching this video, yeah, this problem got me. Sorry about that, guys. So everything has to be, well, sort of. This is correct. So I will leave this in, this answer won't be correct. Let's just fix this very quickly. So the only thing that will change is that you have to square this, right? So always check your work. You see what happens? It's because there's too many variables. So then obviously I will get confused at some point. 1/2 of the mass cancel, V2 initial square was 4m squared V squared divided by 9m squared. So what I'm gonna do is, because since I need B2 final square, I'm just gonna write here B2 final square is 2LG minus half and half minus 2M squared V squared over 9M squared. So I have this relationship. And that's okay, because then here, B2 final square was LG, the condition, right? M squared over R, yeah. So LG is equal to that will stay there, that was here, so 2M squared B squared over 9M squared minus 2LG. Yeah. So LG is equal to 2M squared V squared over 9 big M squared minus 2LG. But there was a 4. Wait a second. Don't I need to multiply by 2 now? So 1/2 of that, 2LG plus 1/2. I half it to minus 2 multiplied by 2. So this should be 4. Yeah, because there's a half there. 4 minus 4. So everything was similar. It was just square now. Right? That makes sense now. Multiply by 2. Yeah. That should be. So 4 and 4 here. All right, so the answer was very similar, right? So 5LG is equal to 4M squared V squared over 9M squared. Then from here, V is equal to 45, the square root of 45 LG divided by, so 45 LG M, I took the square root of that, M squared is M, divided by 2M. There it is. That's the answer. Always check your work, especially when you're working with variables. Okay, so that was a more complicated problem, mostly because of the little things that you can miss. Like, for example, I first missed a little v, so that was easy to fix. But then here, I forgot to square it, so that changed the whole answer, right? So let's double check. 1/2 of M B2 initial square, which is this. A half there, that will give you 2 when you simplify. MG12, M cancels, that's fine. 1/2, and that's V2 square, V2 final, which is the velocity here. You have 2 times all this minus that, but you have a half, so that's why you multiply by 2. 4M squared, V squared over 9M squared minus 4LG. When it goes to the other side, that's V2 final square. I leave it like that because on the condition I have the square. MV squared divided by R, which is L, equals to mg. So you have V2 final square. Then you combine this with that, and you get this equation, and you get the value of V in terms of L, G, M, and N. All right. So if you have questions about this problem, don't hesitate to send me an email. All right. But yeah. Okay. All right, guys. I will leave it like that, and I will see you guys later.